Alright everybody, this is a follow-up video on derivatives. In the previous video we had discussed kind of general concepts of the ideas behind the math involved for derivatives. This is actually going to present you with the code, and hopefully when presented with the code it gives you a even more complete way to connect the dots for the concepts. So I'm going to go cell by cell, and hopefully by the end of this you have a very good understanding of kind of the background of derivatives. So first we're going to import a couple libraries. One is pyplot from the matplotlib library. This is just going to allow us to graph something. So very simply just for graphing purposes. Then we have this derivative function out of the scipy library, and that's actually just going to allow us to check our functions that we're going to use here or create here. So go ahead and load those in. The next line, we're going to actually create a list of numbers, 0 through 10. It doesn't matter what these numbers are, but I use 0 to 10 just to keep it simple. Those are going to be our input values, so our x's. We're going to input all these numbers into a function, and we're going to see them plotted. What having a list of numbers allows you to do is this kind of neat notation where you create a for loop. The x is each item in my x's variable, and I've just notated it as an x. And then what I'm going to do in that for loop is square each x. So that's going to give me output values for x squared. And then I can plot that, and you get this lovely exponential here. So you'll notice at 0 I have the value of 0, at 10 I have the value of 100, and it has a nice exponential rise to it. So then what we want to do is actually try to calculate slope at various points. And in order to do that, we're actually going to write functions for the limits, and we're going to do kind of a geometrical viewpoint as well. And then we're also going to check it using the derivative function that we loaded in. So first we're going to use limits, and limits are where you're still taking that very basic idea of the output of the y's over the output or over the inputs of the x's. So rise over run, or the difference in y's over the difference of the x's. In order to do that, I'm going to input one x value, and that x value is where I want to find the slope for it, right? I'm going to input a function. In our case, it's going to be x squared, and we're going to create that further down. And then we need to create an h value. H is the sliver of a value I'm going to add to my input to try to get these 2 points that are very, 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 very close together. So normally you would take 2 points like 9 and 10, and you would calculate a slope between that. But when your graph curves, you can't take points that are too far apart. So the closer you can bring those together, the more accurate you will have for your slope. So our h value is going to be incredibly small, and we're going to output the value as m, just for the reason that y equals mx plus b is your basic line formula, and m is the slope. So we'll go ahead and create that function. Next, we're actually going to create another function that views it kind of geometrically. And the reason for that is, especially for our version, we're using x squared. X squared is literally a square. And when we add a sliver of a value to it, we're adding a sliver on the base, and we're adding a sliver on the height. And we can calculate the areas of those slivers we've added, add them together, and we can get that basically the slope geometrically in a way. Where the first thing we calculate for is dy. dy is the slope of the output. So from output point 1, or excuse me, not the slope of the output, it's the difference of the output. And what that gives you is, for every input change, my output change is changing by so much. But slope is not just change of the output, it's the change of the output over the input, where i's over run, or difference in y over difference in x. So what we're going to do is calculate this sliver, which is going to be of width x and height dx on one side, and the opposite, of height x and width dx on the other side. Add them together. That gives us the difference in output, and then we're going to take that difference in output and divide it by the original difference that we had. That gives us, again, m, which is going to be our slope. This is, if it's a little confusing here, go back to the other video and it'll actually explain it in a little bit more detail. And then we're going to finally, so let's go ahead and run that, create that function. And again, we're assuming the function is squared. You can do this a little, I didn't want to take too much time doing this, but you could probably write an if case for whatever power your function is. So, and then we're going to create our actual function, which is going to be function squared here. It inputs a value, and you're going to output a squared value of that. So it's just y equals x squared, and we're going to return that output. Okay, so now we're going to get into it. I'm going to pick x as the point that we're trying to locate the derivative for. In this case, I'm just going to use 3. We can use whatever we want, but I'm going to use 3 here. And then for dx, which again, dx or h even, is actually exactly the same idea, the same exact function. So let's actually specify that just to keep it. So we're going to keep them the same, and for my limit function, instead of putting dx, I'll put h. So that way it doesn't mix up here. So I'm going to create a very small value for dx and h. Ideally, it's much smaller than this, 10 zeros and then a 1 after it. But in our case, we're going to use it as 0.01. It's a more conceivable idea. It's still very small. So that gives us what we need there. So now I'm going to go ahead and call my limit function, which was right here. Again, it's the difference in these outputs here over the difference in the inputs. I'm going to go ahead and call that with my x value of 3 and my h value of 0.01, and the function is going to be y equals x squared. So let's go ahead and see that. We should get something, if you guys are familiar with the general rule, I think it's the power rule or something like that. You take the squared part, bring it down, and it becomes 2x. That would be your derivative for this, so 2x. Because x is 3, 2x would be 2 times 3, that would be 6. So we're aiming to get a value that should be close to 6. And we did. We got 6.00999999. So very close. If we shrink the 0.01 to 0.001, ideally we would get even closer to 6. So we get closer and closer and closer and closer and closer to 6. So next we actually want to run the geometric function. The geometric function is going to do the exact same thing, but I don't actually have to input the function because I'm already assuming that it's x squared. I could go a little bit more deep into that function and try to create it a little bit more open-ended, but I'm not going to do that now. So again, we're putting in x equals 3, and the dx is a very small value of 0.01. So again, we should be close to 6 here, and we get exactly 6. So wonderful. That is very good. And then finally, just to check our answers here, there's the function in the SciPy library, again right here, scipy.mis for miscellaneous, I assume, and you import derivative. So we're going to go ahead and call derivative, which takes a function, takes an x input, and then takes a dx value. So very similar to what we did here for these functions here. So again, we should get something close to 6, and we get 5.999999999. So any one of these versions works arguably equally well. They each take a different assumption going into it, but it gives you the output needed. So hopefully this, in combination with the previous video, which kind of lends the conceptual idea of derivatives, gives you a pretty firm grasp of what's going on when you calculate a derivative.